Well, welcome everyone. This is the fourth in the series of Further Maths student revision tutorials. And this one focuses on annuities and perpetuities. That's me, David Tynan, and I'll be presenting today. And our topic is annuities and perpetuities. So without further ado, you'll notice that the problems all centre around a gentleman called Hank. So let's go to problem one. So in problem one, we outline that Hank is a very financially focused young man, and by the time he's 20, he's already saved $35,000. And planning for the future, and in fact planning for retirement a long way ahead, he decides to put that money in an annuity investment account, which gives 5.2% compounded fortnightly. And as well as that $35,000, he decides he'll put in another $150 every fortnight into that investment. So we need to work out what's the recurrence relationship. And then if he kept doing that until he was 70, which is 50 years on from his birthday, the 20th birthday, how much would he have in his account? And there's a big assumption that the interest rate stays the same, but let's just say that the average is still 5.2. And then we look at a modification where he instead decides to pay $200 a fortnight instead of $150. And he does that for the entire 50 years. So let's go to the calculator now and have a look at this. And you might have already had a go at this, but let's begin. So first of all, in order to work out the recurrence relationship, we need to know what the multiplier is, the big R value. So in this case, it's 1 plus, and then we'll just do the fraction template, and it's 5.2. 5.2 divided by 26 divided by 100, whoops, and enter. So 1.002. Now I won't write out the recurrence relation here, but I'll just say it out loud. So we expect that the balance at the n+1 period to be 1.002 times the previous balance, or B of n, plus 150 because he's putting in 150 every fortnight. And the initial value, B0, is 35,000. So that's A taken care of. And now we'll just go into the TVM solver to see how the annuities work. So I got pretty good at doing menu 8 for finance and 1 for solver, and you probably have as well. So let's enter in the right things. So it's 50 years and 26 periods in a year for the compounding. The rate is 5.2. The present value is the lump sum that he put in, and it's written as a negative because we're giving it to the bank. It's leaving us and going to the financial institution, so it'll be a negative. And in addition to that, he's making a payment of 150, and because it's a payment to the bank, it's leaving us and going to those. It's a negative experience, so we write negative for that. And we're interested in what the future value will be, but before we do that, we need to make sure that we note that the PPY is 26, as is the CPY. So we'll go back down to future value and solve for that. So that seems quite a large number, but remember you're talking about 50 years hence. $1,402,171 roughly. So that's the answer to B. And then for C, what we're what we're doing is just making a small change to the payment. And it's quite a striking difference. If he was able to find another $50 a fortnight and change nothing else, it goes from 1.4 million up to 1.7 million, roughly. So it's quite a striking difference with just an extra $50 a fortnight. 25 bucks a week more, and he could have ended up with, to be accurate, about $310,721.61 greater. So that is the story of problem number one. But we're going to approach this problem slightly different now. We're going to look at back to the original scenario for problem two, but let's switch back to problem two to have a look at the nature of the second problem. So if he keeps with the original investment strategy, which is the paying the $150 a fortnight extra, what would it mean if he decided to retire earlier than 70 years? How significant would the reduction in the final balance of his annuity investment be? And also we look at how much the investment or the balance of the annuity investment increases in the last number of years, because as you'll see, it's quite a striking difference. So to analyse this problem in a slightly different way, we're going to use a program called Annuity. And Annuity is a little bit like, for those that saw the earlier video, it's a little bit like a mort loan, but for annuities. So let's just try to load that. I probably should show that in this file, which will be on the Google Shared Drive, you'll be sent a link to this file, so there's no need to worry about that too much. You can get that file after the webinar when you get a follow-up email. So I'm going to press the var key, which shows me that there is a program called Annuity. So if I press Annuity and then just close the brackets and press enter, it's running a program. So the principle, if you remember, is the original lump sum that was put in. We're not making this negative. We're just talking about the quantity of money rather than the direction, it being positive or negative. So that's the principle. And the interest rate was 5.2. The annuity out, so that means is Hank taking money out of the investment account? No, he's not. So we can put a 0 there. And is he putting anything in? Yes, he is. He's putting $150 in every fortnight. And the number of periods that we want to show is the entire length of it. So 50, lots of 26, and that should take him up to an age of 70. And there are 26 compounding periods and payment periods per year. So this generates a massive matrix of results and highlights what we did find with the TVM solver, and that is that he ends up with about 1.4 million. So there are some nice things about this program outside of generating a history, if you like, of all the transactions, in this case all the fortnightly transactions. There's 1,300 of them. So it does allow us to analyse further. So for example, we could go to a scatter plot and put the number of the payment and the balance of the payment, and we can see the real curvature in how the balance changes over the 50-year period. Now, there are a lot of points here, 1,300 points. So I'm not going to try to click anything, but if I go to the end, you'll see that final point there. But even more importantly, if you look at the curvature right at the end, it's growing most quickly, or the gradient is steepest towards the end of the life of this investment annuity. So that's not the end of the usefulness of this, because we are able to check the balance. So I'll go back to VAR so you can see the variable, and you'll notice there's a variable there called balance, and that's really all the entries in this final column, the balance column. So if I said I want the balance of the last value, I would put square brackets. Square brackets are because I'm referencing a particular element in a variable called balance. So if I did 50 times 26, it should give me, as it does, the final balance at the end of the 50 years. Now, the questions that are being asked are, what happens if he does 60 years, you know, if he retires when he's 60? So similarly, I could get that value and change it from, so when he's 60, that means the investment account's been going for 40 years. So that's quite striking. So if he decided to retire at 60, he wouldn't get 1.4 million, he'd only get 803 odd thousand. Would it be a little bit better, or we suspect it'd be a little bit better if he tried it for 45 years? So we can change that. And you can see that he's cracked the million. He's got over $1 million in his investment account, but it's still quite a lot less than if he had worked until he was 70, that is for 50 years of this account. Okay, now the second part of that question is to say what's happening in the last three years. We could do more years, but let's just focus on 3 years. So when he's 67, that's 47 years of the investment. So we'll just do the same thing, but do it for 47 years. And we can see that it's about 1.19 million in his account. And the question's really asking, how much does the investment balance jump in those last 3 years? So what we'll do is type in balance and square brackets for the reference. And what we'll, instead of just putting in the values directly, we will put in brackets year plus 1 times 26. And we'll take away the balance the year before, square brackets, and it'll just be year times 26, 26. And we will put a condition on this. So for those that aren't familiar with that, so if you press Control equals, you'll get this vertical line, and the vertical line allows us to put a condition. And the condition that we're going to put is that the year is 47. So let's just slow down a little bit. That looks complicated, but what you're saying is that from his 47th year of that is from when he's 67 to when he's 68, the balance has increased by 67,398 in that year. And so we can do a similar thing to see what happens the next year just by changing 47 to 48. So we see what happens next. And so it's gone up to nearly 71,000 in that year. So it's quite striking how the balance is increasing in that last little while, as we saw in the graph, and now we're seeing in individual figures. And here's the last year. So from when he was 69 to when he turns 70, it goes up by nearly 75,000. And this helps explain sometimes why people are reluctant to retire early, because financially they are making, or their superannuation, as an example of an annuity investment, is making so much money in the last few years that it works against them if they retire, even if parts of them would like to retire. Okay, so I think that that is the end of problem 2. So let's switch back to PowerPoint and have a look at problem 3. So Hank's now considering what will happen or what he will do when he gets to the age of 70 and stops working and decides that he transfers the balance of this annuity investment into a retirement fund, which he's going to manage. And it's very difficult to predict what the interest rate will be, 50 years hence from when he was 20. But for the purpose of this analysis, he's decided that it's probably going to have an interest rate of about 6% per annum, compounded monthly this time. He wants to live off this retirement fund for the rest of his life, which is quite reasonable. The problem with that is that it's tricky to know how long you're going to live. And so initially he considers, well, I'm just going to convert it to a perpetuity, which is a sort of account which allows you to get a regular, in this case, monthly income from your fund, your retirement fund. And it must be such that the payment can continue indefinitely. Okay, so we'll see what happens when he tries that. And after that, we'll consider if he really wants to have $9,000 a month for the rest of his life, how much would he have had to have, and has he got enough in his retirement fund to achieve that? Okay, so let's go back to the calculator. So we'll go into the finance solver, which is menu 8.1. Okay, and now because it's a perpetuity, the end value is not really very relevant because you're going to be able to do this forever. So let's make the other changes. I think we said it was 6%. And the amount that he had in this account was the 1.4 million. So I'll just put that in. It's a minus because we're giving it to the financial institution. 1,402,170.67, just rounding it to the nearest cent. And the key thing with a perpetuity is that you must have the PV and the FV being the same value, even though they're negatives of each other. You do want that number to be the same, 1,402,170.67, and we have to change this PPY and CPY to 12. And the question is, what is the amount that he would be able to draw each month so that he could do that for as long as he lives? So if we solve for that, we'll see that it's a positive 7010. So about $7,000 is how much he could afford to take out each month, or receive as a payment each month, and still keep the balance of the account the same. Which means that if he does die, it doesn't matter when he dies, there's still 1.4 million in the account, which he might decide that he wants to share with his beneficiaries that he's listed in his will. But that's the advantage, I guess, of a perpetuity. So 7,000, it seems like quite a lot of money, but we really don't know 50 years hence whether that's going to be enough. And so we now move to the second question, which is, if he decides that 7,000 isn't enough, but he wants to have 9,000 here, then the question is, how much would he have had to put in the bank so that he could do that? And this is a slightly confusing thing for further math students because they have formed the belief that the TVM solver would do this. But if you look at the solver template in front of you, the finance solver, you'll see that the PV and FV are not known. That's what we've got to find. One is the negative of the other, but we really don't know either explicitly. And the solver can't really do that if there are two things unknown. In fact, I believe it just gives an error. Unable to calculate it. So this is one of the limited number of cases where you do need to try to do it outside of the solver. And so if you think about PV equaling FV, what you're really trying to say is, I must make the payment the same as the interest generated. So let's see how that works. So we can solve where the interest that would be payable each month multiplied by whatever the amount that's in there, which I'll call the principal, must equal the 9,000 that Hank requires. And we solve that for the variable called principal. Wow, so that means he would need to have put into his retirement fund not the 1.4 million that he put in, but 1.8 million. And I believe that's the end of problem number 3. Okay, so let's go to problem number 4. And the final problem is Hank considering an alternative, which is not a perpetuity, and he's going to punt on how long he's going to live. He reckons that, okay, I'm 70, when I'm 70, I'm going to take a punt on doing it for 25 years, so I'll be 95. Can he get $9,000 a month for 25 years after he retires? Okay, so transfer back to the calc, and we can now go back into the solver menu, finance solver. Okay, so we want to calculate how long he can get 9,000 for. So in this annuity scenario, so the interest rate is still that, and that is the amount that he did put into the retirement fund. We're saying that we want it to be 9,000 as a monthly payment, and this should be 0. So we want to know for how long can he get $9,000 without zeroing his retirement fund. So if we shift tab back up to the top, and that shows us that it's 302.65. So let's say 303 payments, but they won't all be full. There'll only be 302 full payments. And rather than spend time calculating what that is, I can tell you that 302 payments, oh, well, we'll do it anyway, we've got time. 302 divided by 12 is 25 years, and we'll just take away the 25 and multiply by 12 and see that it's really 25 years and 2 months. So he can last for 25 years getting 9,000 before he zeroes his retirement fund. Okay, and so the final part of that question is to consider what happens with the final payment. Now, he could work out what happens. So let's go back into the solver, menu, finance solver. And let's say it was 302 payments. And the question is, what's left? at the end of 302 full payments of 9,000. And we can see that his final payment, so after 302 payments that are 9,000, there would be a final payment which would be $5,896.68 plus whatever interest that would attract in the final month. So there's a couple of ways to do this, and we did this with the Mort loan, but I'll just move it from here. So if we put it up to the PV, so it's a little bit like saying we've got that much in the account. I'll just remove the extra, remove the extra digits here. That's a minus. And we truly want it to be 0. And the question is, in one payment, what will it be? And it's just a little bit more, $5,926, and that's about 16 cents. So I'll just copy this bit. You don't have to use the TVM solver for that. You could have done the following. It's the balance at the end of 302 payments plus fraction, so it's 6 plus 1 month's interest multiplied by that balance after 302. So that's giving us the same answer. And then just to finish off, because we've got 2 or 3 minutes left, we're going to try doing the same thing with the annuity program. And the principal is $1,402,170.67. The interest rate is now 6%. The annuity out is 9,000. There's no payment in. And the number of periods to show, we're going to show not 302, but 303 payments. And there are 12 compounding and payment periods per year. And then you'll notice that in this particular case, it's saying, oh, I can nearly finish this. Do you want me to adjust the final one? And I'll just say yes. And so with a little bit of a scroll up, you can see the last line there. So at 302 payments, that was the balance. And that's what happens if you did a third payment of 9,000, but that wouldn't be zeroed there. In fact, you'd owe them money. So you can adjust it in the last line. So the 303rd payment is not 9,000, but this adjusted value. And finally, you can see what happens in an annuity when you're withdrawing. There's a familiar curve. However, it looks like it's in the other direction. I'll just zoom out of that. And you can see the curvature of your money. It disappears more quickly at the end. And so that's an excellent point to finish this webinar. And I might just finish by saying that next, in a fortnight's time, we'll be running an extra webinar focusing on the construction of notes pages and some of the tricky things that you might have seen in some of these other webinars, and including things like using library functions, using widgets. So there's a double header in 2 weeks' time where those ideas will be presented. And so that's all for tonight. And we'll see you next time, we hope. Okay.